Hello everyone. Our next topic is going to be traffic equilibrium, and it is related to the previous concepts. First, we are going to use the concept of Nash equilibrium, and in addition we continue with our topic, is the more the better. An application of the traffic equilibrium will be to network design. The main topic on traffic equilibrium has to do with what we call the brace paradox. We'll talk about that. Let's start. So the problem is the following. Let's say that we have a network of roads, and as you can see in the diagram, every car, every driver is moving or try to move from A to B. They can go either through D or through C. At C and D there is nothing there. Everyone is going from A to B. You can go from one road through C or for another road through D. The question is how long it takes to go in each one of the segments. Okay, here we have 4 segments. Now let's talk about the segment A to C. Okay, A to C, and it takes 2 plus 10h. What does it mean, 2 plus 10h? If h is the number of thousands cars on AC. So for instance, if no car is there, h is 0, then it takes just 2 minutes. And every 1,000 cars add to the time, the driving time, 10 minutes. If h is 1, namely that 1,000 cars are going from A to C, it takes 12 minutes. 2 plus 10 times 1. If h equals 2, it takes 2 plus 10 times 2. So this is 12, and this is 22. And if h equals 3, it takes 2 plus 10 times 3, 32, etc., etc. So as you can see, if you increase the number of thousand by 1, you increase the time that you have to spend on the segment AC 10 minutes more. How should I interpret this? I can say that the road from A to C is very short, because if no car is there, it takes you 2 minutes, but it's very narrow. So 1,000 cars add 10 minutes. Another 1,000 cars add another 10 minutes, etc., etc. Let me now move to the segment let me now talk about the segment BC, going from C to B. That takes 48 minutes plus the number of thousands of cars. So first of all, if there is no car, then it takes 48 minutes. Every 1,000 cars add just 1 minute. Let's see, if h equals 1, it is 48 plus 1 equals 49. If h equals 2, 48 plus 2, 50. And you can see it easily, because the coefficient on AC was 10, so it adds 10 minutes for each 1,000 cars. Here the coefficient is 1 times h, which is h, so it adds 1 minute. Similar, if you want to go from A to D on the segment AD, it will take you in a symmetric way 48 plus h. Okay, so again 48 minutes if the road is empty. Every 1,000 cars add just 1. And similarly, dB is as AC, 2 plus 10H. Now 6,000 cars, all the time goes from A to B, either from D or through C, and some cars coming in, some cars leaving, and in the system is all the time 6,000 cars. That's the assumption. So in terms of number of thousands, I have 6. Okay. So now let me first of all clean things. Okay, and let's read together just to make sure that we follow each other. Consider a road network as shown in the next diagram, with 6,000 drivers travel from point A to point B. The travel time in minutes on AC road is 2 plus 10H, where H is not the number of cars, but the number of thousands of cars on this road. If the number of cars on AC is 2,000, then H is 2, and the travel time from A to C is 22. 2 plus 10 times, H is also 2, 10 times 2, 22. Likewise, the travel time on BD is also 2 plus 10H. I take it as a simple example for symmetry. The travel time on CB or AD is 48 plus H on both. What is the travel time of a car that goes from A to B in equilibrium? Meaning that, what does it mean, equilibrium? Okay, before I go to meaning. So let me just clean this. Good. Okay. And now let's talk about what do I mean by equilibrium. So before talking about equilibrium, let's write it again here. And we have 6,000 cars. So suppose that actually 2,000 go to the right, so H equals 2. So the same 2,000 continue from C to B. Now, if 2,000 go to the right to C, how many will go to the left? There are 6,000. If 2,000 went right, 4,000 goes left. And the same 4,000 continue here. So H equals 4. So as you can see, the H varies for segment to segment. It's a little bit misleading that I'm using the same letter H on each one of the segments, but I'm talking about what I mean is H belong to the segment, and it may be for different segments we may have different H. Here is H equal to H2, this is H4 and H4. Okay, so now let's see if I'm one of the drivers that go from A to C and then to B, how long I spend. So the time that I would spend if I go ACB is the following. 2 plus 10 times 2. This is the part of A to C. And then from C to B it will take me plus C to B, it will take me 48 plus 2. Total time 50 plus 22, 72 minutes. Now suppose that I want to go left. T, A, D, B. So if I go from A to D, it takes me 48 plus 4, because the H is 4 now, plus, and that part is going from A to D, plus the part from D to B, 2 plus 10 times 4. That's the part D to B. And this is equal 52 plus 42, 94. So if I hear, let's say by using Waze or other GPS, that it's faster to go through C, okay, then cars that used to go through D will switch now. They'll say, why should I spend 94 minutes? I have an alternative way to spend only 72 minutes. And therefore, cars will start moving, more cars to the right, and therefore the H will start increasing, and on the road A, C, and CB, and H will decrease on the road ADB until no one has an incentive to deviate. This is the case if you don't want cars that went or go left through D to be envy on cars that goes right to C. It must be that the time you spend left is at most the time that you spend going right. But at the same time, for cars that go to the right, not envy the car that goes to the left, they have to spend at most the same time. So to satisfy this, it must be that going left through D or going right through C should take the same time. So this is not an equilibrium. In equilibrium, no one would like to deviate. So everyone happy. If I will deviate, then I will spend at least that much time. And if I deviate from the other side, I would spend at least that much time. So the only way to satisfy is that doesn't matter if you go through C or through D, you spend the same amount of time. That's what it says. What is the travel time? What is the travel time of a car that goes from A to B when the system is in equilibrium? It meaning that traveling through C takes the same time as traveling through D. And now the question is, how many will go through C and how many will go through D? Okay? So actually, since everything is symmetric, it is clear that I mean 3,000 will go from A to C and then to B, and the other 3,000 will go through D. But it's clear. And what happens if it's not symmetric? So the question, how do I solve it in general? So in that case, let me first get, so actually let me, okay, and let me clear this one just to make it nice. I don't know why I cannot do it. Okay, now I can. Okay, fine. So let me put again the diagram, and I want to solve in equilibrium. How many cars will go through C? So I say, let's say that X thousand cars go from A to C. So the same X thousand cars must continue to be. So the H is X. Okay, this H is X, and the same thing, this H is X. So how many thousand are going through D? Well, there are 6,000. So if X of the 6 going to the right, 6 minus X go to the left. Remember, I count everything in terms of thousands. So I have here also 6 minus X. So the H here is 6 minus X, and the H here is 6 minus X. Now I want to say equilibrium condition. Equilibrium condition. So this is to say the time that it takes me to go from A to C to B should be the same time as it takes me to go from A to D to B. let's see what is each time. So let me start with ACB. To go from A to C, it takes me 2 plus 10h, but h is x. This is A to C. Plus 48 plus the h is x to go from C to B. This should be equal the time to go through D. So 48 plus the h, but the h is 6 minus x. This is the time to go from A to D. Plus the time to go from D to B is 2 plus 10, 6 minus x. Because the h is 6 minus x. Okay, just to simplify it, I see that the 48 and 48, 2 and 2 can cancel out. And I have on the left side 11x equals. On the right side, let's start with the x. I have minus x, and if I open the bracket, another negative 10x, so minus 11x. I have, and the number is 6 plus 10 times 6, 66. So I have 22x equals 66, x equals 3, which was clear before, but that is because it's just symmetric. If I change the number to something else, the equilibrium will change, and it may not be 3 and 3 symmetric if the diagram is not symmetric. Good. So now, solution, we did it algebraically. By symmetry, 3,000 drivers will travel from A to B through C, and the other 3,000 drivers will drive through D. Because if x is 3, then 6 minus 3 is also 3. That is, h equals 3, and the travel time is what? So let's see the travel time. It doesn't matter if you go like this or you go like this, because we said it's equal. That is exactly the purpose of this exercise. So how much is it? It's 2 plus 30, because I have 10 times 3, plus 48 plus 3, 51 plus 32 equals 83 minutes. Great. So we know that it takes 83 minutes to go from A to B, and doesn't matter if you go through C or you go through D, it takes 83 minutes in equilibrium. Okay, good. So now, by the way, you can ask why I don't have a way to connect directly. So it is possible that it's impossible, that the case is that you have here big mountains, or I don't know, a big lake, and it's very difficult to go from A to B. Okay, but maybe it may be possible to go from C to D. So it may be possible that I'll go, if I build this road, that I can go like this, and like this. It depends how efficient this road is. Or in that case, I would be able to go like this or to go like this. But this changes the entire picture. Okay? Okay. Good. So here it is. Now suppose the 2 points C and D are connected through a relatively short road, and the travel time on CD is 6 plus h. What does it mean? If the road is empty, it takes you 6 minutes. And every 1,000 cars just add 1 minute. It's quite efficient. So look, I want to say it again. Suppose I'm the only one on the road. I can go from A to B with the new road in 10 minutes. It will take me 2 minutes here, h is 0. 6 minutes here and 2 minutes here. I would be able to go from A to B in 10 minutes. Without this road, I would be able to do it in 50 minutes. 2 minutes here, 48 minutes here. 48 and 2. So it looks promising to build this road. Now, just for simplicity, I'm assuming that it's a one-way road. As you can see, the arrow is like this, and you cannot go DC. By the way, you can allow that. In any event, nobody will go from D to C if you allow it, because that will be intuitively 48 minutes plus 6 plus 48 minutes. You know, if you allow it will go like this, it's quite crazy, because it would take 96 plus 6, 102 minutes if it is empty. But you can prove that nobody will take this road. But just to make life simpler, we assume that going from C to D is one way. Okay, let me read it with you. Now suppose that the 2 points C and D are connected through a relatively short road, and the travel time is 6 plus h. For simplicity, assume that the road CD is one way, and one can only travel from C to D, and not from D to C. That's what I want. You can travel on every segment, but on the segment you can travel from A to C, from C to B, from A to D, from D to B, and from C to D, not D to C. Okay. Question. What is now the equilibrium time? Okay. The equilibrium travel time. So, good. So that's the question. So let me first, instead of giving you the solution right away, let me work it out with you. And for that, I'll clear this one. Great. And now I'll copy this diagram. So it's here. Everyone is traveling just from A to B. So now there are 3 alternative ways to go. One is to go AC and then CB. The other alternative going AD, and then DB. But now you have a third alternative. I can go from A to C, from C to D, from D to B. That was 6 plus H. And I want to solve it. So how many cars will go, let's say, on the segment AC? I don't know. I put X. So the H is X. So how many will go from A to D? Remember, total number of cars. Oh, I lost it now. No, I got it. Good. So total number of cars is 6,000. So this is 6 minus X. Okay, so X 1,000 cars are going from A to C. But then they split. Some will go to D and some will continue directly to B. How many goes to D? I have no idea. I put Y. So the H here is the Y. So how many will go from C to B? If X went from A to C, and out of this X, Y went from C to D, so how many left to go from C to B? That is X minus Y. So this H is X minus Y. I repeat, X 1,000 go from A to C, and Y 1,000 out of this X are going from C to D. So what left to go from C to B is the X minus Y. Good. So the only thing that left to see how many cars are going from D to B. So look, 6 minus X are going from A to D. And then from the other side, from C to D, another Y. So actually I'm getting here 6 minus the X plus the Y that comes from CD. So the H here is 6 minus X plus Y. And now I have to find 2 equations with 2 unknown, X and Y. Equilibrium, I'm writing equilibrium condition. Equilibrium condition. So first of all, like before, going through from the time takes to go from A to C and then to B equal the time to go from A to D and then from D to B. So let me write it down. Time to go A, C, B equals time to go so A, C, B equal time to go through D. This is first one. I need another one. So I can say, I don't need to go to do all the way, but I can say the time to go from A, C, and then to D is the same as to go directly from A to D. Why? Because if it is shorter to go in time, to go from A to D directly, then cars will start moving from ACD to directly AD, or opposite. If it is shorter in time to go to D through C, then cars that go directly will start switching to the right to go not directly because you can save time. So it must be in equilibrium that A, the time to go ACD equals the time to go AD. I could write another equation, but I don't need. I need just two. For instance, the time to go from C to D and then from D to B equals directly from C to B. But let's stick to these two. So let me write down what is the time to go ACB, condition number one. So let me write it. Condition number one is the following. AC first. AC is, so I'm doing condition number one. So I have 2 plus 10h, which is x, plus this is to go AC, plus to go CB, 48, plus the h, which is now x minus y. This is going C to D. Must be equal then the opposite sides. A to D, 48 plus the h, which is, what is the h? 6 minus x. Plus 6 minus x. Plus this is A to D. Plus C to B. Plus going from D to B, it is a little bit longer. It's 2 plus 10 what? The number of thousand cars, which is 6 minus x plus y. Let us rearrange terms, and to make it simple, again, I cancel 48 and 48, 2 and 2. And what is on the left side? I have 11x, 10x plus x, 11x minus y equals, let me start with the x. I have minus x and then minus 10x minus 11x. How many y's I have? Plus 10y. And what about the number? I have 6 and I have 10 times 6, which is 66 together. I take all the variables to the left. I'm getting 22x minus 11y, because I take the 10 with a minus sign, equals 66. Let me divide everything by 11 to make it simpler. I'm getting 2x minus y equals 6. Here is number 1. Now let me go to number 2. What is number 2? Number 2 is, and this part was from D to B. Number 2 is ACD, okay, ACD. I'm moving now to number 2. ACD is 2 plus 10x, this is the AC, plus CD, which is 6 plus the H, which is Y, this is C to D, equals going directly 48 plus the H, which is 6 minus X. This is to go directly from A to D. Good, the 6 and the 6 cancelled. Let's move So I have 11x plus y, or 11x plus y equals 46. 48 minus 2, 46. So I got two equations with two unknown. If I sum it up, the two of them, the 2x plus 11x, adding up one and two, what do I have? 13x. 13x, the y cancel out, equals 52. X is 52 divided by 13, 4. But if I know, look on equation 1, if I know that x is 4, then I have 2 times 4, 8, minus what give me 6, y equals 2. So now I can tell you, 4,000 will go from A to C. The y, 2,000 out of the 4 will go left, and the other 2,000 will continue directly to B. And similar, I mean, 6 minus x is 4, x is 4, so 2,000 will go from A to D. They will combine with the other 2,000 that comes from C to D, from to D. Altogether in D, there will be 4,000 cars moving from D to B. Okay, very good. Let me now, so this is it, and what I got, actually what I prove it to you, it's not on the slides, but this is the solution. Look, x is 4, this x is 4, this y is 2, and that's it. I don't need more, because if 4,000 go from here and altogether I have 6,000, it must be that the rest, the 2,000, go from here. Now 2,000 I'm coming from C, and another 2,000 I'm coming from A. Altogether 4,000 are going from D to B. So this is the situation. Good. After we figure it out, I want to see what is the time takes to go from A to B, let's say through C. Through C it is 2 plus 10 through C. 2 plus 10 times the number of 1,000, which is 4, plus 48. I'm going now ACB. Okay, let me say ACB. Plus 48 plus 2. Okay, so I have this one on AC and this one on BC. 50 plus 42 equals 92. Wow, surprise, but hold on. Let's check now the time to go from A to B through D. So if I look on ADB, the time is what? 48 plus 2. This is to go from A to D, and then plus 2 plus 10 times 4, again 92. So there's no car envies that goes through C, envies the cars that goes through D, because they take the same time, and vice versa. But maybe to go, what about ACDB? I mean, what about going like this? It takes 42 to, so ACDB. It takes 2 plus 10 times 4, plus 6 plus 2, this is the road CD, plus another 2, plus 10 times 4. What is it? This is 42, 50, 92. That's an equilibrium. No, doesn't matter how you go, it takes the same amount of time. But before we had this road that connects C to D, before we had it, let's say without this, 3,000 went like this through C, and the other 3,000 went like this, and it took only 83 minutes. So now, after building a very efficient road, what happens to all drivers? Everyone spends 9 minutes more It used to be 83, and now it moved to 92. We build a road, and it's not inefficient, very efficient road. If nobody on the street, on the roads, you do it in 10 minutes. 2 plus 6 plus 2, 10 minutes. So, excellent. We should be happy. But even if the road doesn't cost money to build, you don't want it. Because is the more the better? More roads sometimes are worse. Situations like this were first observed by Brace. That's why it's called the Brace paradox. The story is about Stuttgart in early 1930, 32 or something. Student took statistics and measured how long it takes for a car to go from one side of Stuttgart to the other side of Stuttgart. And they had quite a good estimate in certain hours in the morning. One day they close a road for construction, and they anticipate that everyone will have to spend more time. And they realize that everyone is now spending less time, even though they close the road for construction. And what happened? I mean, at the beginning they were sure that they made a mistake. But then when you look on it, you realize that if I take, it's like this diagram. It takes 92 minutes, but if I take this road out, it will take only 83 minutes. So you should not be surprised that sometimes when you close a road, that everyone is happier. That's the paradox. Okay? So now you may tell me, well, you may say, well, you know, it may be not that efficient, this road, okay? It may be that actually maybe if it instead of 6 plus h, you put here 4 plus h, you do much better. So let's now look on it and say, you know what? Suppose they build a miracle road. What does it mean, a miracle road? It takes no time to go from C to D, 0. In reality, it's impossible, but let's just for the sake of intellectual curiosity. What happens if I put, instead of 6 plus h, I put 0? Well, you may be surprised or maybe not. It can be shown easily solving the two linear equation as before, with two unknowns, that this is the worst case scenario. Now the time is 98.54, so not 83 and not even 92, it is 98.54. Meaning the more efficient is this road, the worse every driver is. And I want to say, what happens here? Okay? And by the way, I think that what I want to say now, it's not on our slides. So this is another example. And let me talk, trying to explain what's going on. So let us say the following. Suppose, now, just as an illustration, I call all the driver to come to a big stadium. Okay, by the way, when I say 6,000 every minute, that means that maybe altogether in the morning you may have 1 million cars, because cars come, cars go, but all the time you have 6,000 in the system. Okay, so let's gather all the drivers in a huge place. And then I'll take the microphone and I'll suggest them. Ladies and gentlemen, this road, the 0 road, is actually very bad. Okay? It brings, I mean, it may make us drive 98 minutes from A to B. I suggest nobody is going to use the road CD. Do you agree? Yay! Everyone is saying yes, yes, we agree. Okay, so the next morning, by the way, if they are not going to use it, I just want to remind you, in this case, if there are no road from A, C, B, D, this was 2 plus 10H, this was 48 plus H, this is 2 plus 10H, and this is 48 plus H. In this case, the time in equilibrium is 83 minutes. So we expect, if this is the case, nobody takes it. In equilibrium, it will be 3,000 will go from here, 3,000 will go from here, and 3,000 will go left, 3,000 to get 83. That was the situation in the beginning, okay? If you remember, here it was, this was the scenario, and T was 83. Good. So let's not use it. So we go. In the next morning, after our decision, I'm one of the drivers. I'm taking the road AC, and all of a sudden, when I'm getting to C, I cannot, I cannot not taking the road. Sorry, this is D. And remember, there is a road here of 0. I'm the only one taking it. Okay, I'm the only one. It's unfair. We'll handle that point in a second. But if why do you care? Why do you care? Because how long I'm going to spend. So Yair, my name, is the only driver, if you like, nasty driver, that deviates. Deviates in the sense that I take the road CD. Deviate to CD. How much Yair will spend? Yair spends, well, 2 plus 10H, H is 3, 2 plus 10 times 3, plus 0, because I jump from C to D, no time, and from D to B, another 2 plus 10 times 3, 64 minutes. So I save, Yair saves, instead of 83 minutes, he goes 64 minutes. Yair saves, and what is it, 19 minutes. What's wrong? What do you care? You go, I'm the only one. You don't like the fact why you and not why me and not somebody else? Okay, I agree. We take a lottery. Let's say that the one was Alice. Alice was selected at random, and Alice has the right now to go from C to D. Alice is going to save 19 minutes. Why do we care? Everyone has the same chance of being Alice, and so you should not complain. Moreover, I can tell you, Alice actually, the saving is more than 19 minutes. Why? Because there were 3,000 cars here. Together with Alice, 3,000 from A to C. Now that Alice went to the left, there are, instead of 3, there are now 2,999 cars. And in terms of how many thousands I have not 3,000, but rather 2.999. So actually, on the road CB, on CB, the time takes on this road reduced by very little, but reduced by how much? Instead of it was 48 plus 3, now it's 50.999. So it was reduced by 1/1000 of a minute. Very little. But how many people are going there? 2,999. Total saving. This is every car saves 1/1000. Total saving is 2,999 times 1/1000 each one saves. It's approximately 3 minutes. So total saving, Alice saved 19, the other saves 3, 22 minutes. It looks nice, very nice. They saved 22 minutes. Why should we be angry? Well, should we? And the answer is yes. Because now I can tell you what is the damage that Alice, or Yair for that matter, inflicted on all others. So now I want to talk, there is a saving, damage. What happens is that when Alice moved from C to D, the number of cars now is not 3, but rather 3,001. So in terms of H, it's 3.001. So now on DB, every driver spends more. By how much more? Instead of 3.3, now you spend 2 plus 10 times 3.001. But remember, now you multiply it by 10, not like here where it was 1H, it's 10H. So if the H increases by 1/1000, the 10H increases, spends 10 times 1/1000 more. What does it mean? Namely, 1/100. How many drivers are going there? 3,001. Total damage, 3,001 times 1/100 is approximately 30 minutes. So on one hand, by not obeying our agreement, the saving was 22 minutes, but on the other hand, we inflicted a damage of 30 minutes. So net damage is 8 minutes. Net damage 8 minutes. But once you see Alice going left, or once you see Yair goes left, then another one also will go left, and another one will go left, and then everyone will be in equilibrium where everyone is going to spend how much? 98 minutes. So if you are talking about even once 6,000, but you have many 6,000, let's say million, 100,000 going through these roads, and instead of 83 you have 98, 15 minutes. So the beginning 8 minutes and more people are coming here, the total damage starts increasing. And what will be the total damage? 98 minus 98.54, let's say, minus 83.15 times the number of drivers that you have. So if you have 100,000, then the damage in terms of minutes is 1.5 million minutes. It's a lot. So you can see that actually this road, how the damage it causes for every driver that starts going from C to D. The beginning 8, but it increases and increases. So this in a sense looks a paradox. When you think of it, this happened. Don't expect an equilibrium to be efficient. We talked about it. Look on a prisoner's dilemma or others. They should not, equilibrium may be efficient, may not be efficient. It depends on the situation. Okay, I think that we exhausted that example quite a bit, and I want to move on to another example of a different type. So example 2. In example 2, I have, again, going from A to B, either through C or through D. But now I tell you some differences. If a car goes from A to C, forget about now these numbers. If a car goes from A to D, let's say, it takes the 45 minutes, no matter if there are 1,000 cars here, 2,000 cars, 4,000 cars. Here I'm assuming that the flow is 4,000 cars going from A to B. In the previous example, it was 6,000. Let's do it here with 4,000. So what does it mean on the road AD? It is very wide. It's not sensitive, it's insensitive to the number of cars. However, and the same thing is the road from C to B. However, the roads from A to C or from A to C or from D to B, it's another story. Now I don't count the number of thousands of cars, but rather the number of cars. So, if the number of cars here is X, it will take me X divided by 100. That will be the number of minutes it will take to go from A to C. And then from C to B, 45 minutes, fixed. Similar here, but it's not the same X. This X refers to the number of cars on this segment. And this X refers to the number of cars in this segment. So let us do, here take an example. So we have 4,000 cars, and let's say 3,000 goes from A to C. All these 3,000 continue to B. And then I have from A to D the rest. I have total 4,000. If 3,000 go here, 1,000 will go here. And all these 1,000, they continue to be. There is nothing here and nothing here. It's just that you take... It's just that you take, when you come here, you take a right, and when you come from A to D, you take a left. Okay. So let's do, what is the total time now? The total time to go A, C, B, so to go to B, but from C, is what? Is 3,000 divided by 100 plus 45. 75 minutes. And the total time to go through D takes, I have only 1,000. So first of all, 45 doesn't matter what is the, how many cars are there. But going from D to B, it takes me 1,000. The X is 1,000 here, divided by 100. It is 10, so it is 55. So drivers will realize very, very fast that actually it takes, it takes less time to go through D than to go through C. 75 minutes, relative to 55 minutes. So watching the ways, they will understand it, and cars will start switching from going through C to go through D. So more cars will go through D, which will cause longer time to spend on this road, and fewer number of cars will go through C, which will reduce the time spending there. Until when? Until it reaches a balance. Since it is clear here since it is symmetric like before, then it's clear that 2000 will go from here and continue, and 2000 will go from here and continue, and therefore it will be 2000 divided by 10, 20 minutes, plus 45 minutes, the time will be 65 minutes. Okay, suppose that, I don't want to say that this is by symmetry, so I want to work it out algebraically, because tomorrow you will get a different diagram or non-symmetric diagram. It's very easy. I say equilibrium condition. If x, let's say x goes from here, and the same x continue, and if this if x cars are going from A to C, 4,000 cars minus the x will go from A to D and will continue to B. So I can find the equilibrium condition is the time to go ACB equal the time to go ADB. The time to go ACB is what? Is x over 100 plus 45, and equals the time to go ADB is 45 plus going DB, it is, I have to replace the x by how many cars I have here? Plus 4,000 minus x dividing by 100. So this and this cancelled. I multiply by 100, and I'm getting that x equals 4,000 minus x, 2x equals 4,000, x equals 2,000. So 2,000 will go from here and continue here, 2,000 will go through D and continue to B. Okay. So actually, probably I said it. And if it is, since the network is symmetric, I don't assume anything. I proved it. But since the network is symmetric, in equilibrium, half of the flow, 2,000 cars, will go through C, and the other half through D. The driving time is what? Put here, this is the driving time, or this, they are the same. So put here x equal 2,000, you get 2,000 divided by 100, plus 45 is 20, plus 45 is 65 minutes. By the way, if it would not be symmetric, let's say that I have this diagram. And let's say still 45, 45. You know what? I'll put here 40. And this is A, and this is B, and this is D, and this was C, and this was x over 100. And let me say that here I have x over 200. How many will go? And there are 4,000 cars. And now x is not the number of 1,000, but the number of cars. As opposed to the previous example where h counted the number of 1,000 of cars, in this example, the x measure on the road the number of cars. Okay. So now I can say how to solve it. So again, the same condition. So ACB, it will take x over 100 plus 45 should be equal to 40 plus how many? Okay, so if x cars going here and continue here, then I have 4,000 minus x here, and all these 4,000 minus x continue. So I have x instead of the x, plus, here doesn't matter, it's 45 fixed. Here it's 40 fixed, doesn't matter, But here, in the number of cars is not x, is 4,000 minus x. Divide by 200. So first, this and this, I left with 5. And I multiply everything by 200. So I get 200 divided by 100, 2x, plus 200 times 5, it is 1,000, equals 4,000 minus x. 3x equals 3,000. X is 1,000. So actually 1,000 will go like this, and 3,000 like this. Okay, let me now change everything because we solved it. 1,000 and continue, 3,000 and continue. And by the way, how long it will take? It doesn't matter if you go from here or from here. That's the entire exercise. It's the same. So let's put the 1,000 here. It's 10 plus 45. T equals 55. How come that it's shorter? Because look, first of all, the time here is half of the time here. Here you divide by 100. Here I divide by 100 and then divide by 2. Or divide by 200. So this is half times with the same number of cars. Here you spend half the time that you spend here. Also, this is shorter, 40. So you see, I mean, this is not symmetric. You solve it in this way. Good. Now I want to say, if 65 minutes takes for every car in our original, so let me take it out. So our original diagram, in our original diagram, 65 each. Okay? It's not this one, 2,000, 2,000 each one. Then you can say, how many cars I have? I have 4,000 cars. Each spends 65. So the total number of minutes that they spend is 260,000 minutes. So let me simply, this is the time takes for every car times the number of cars. This is the total. The equilibrium here is efficient in the sense that there is no other traffic pattern that reduces, should be the total time spent on the roads. How do I know? How do I know that? So we do an example. Okay, here's the example. Suppose that 3,000, not an equilibrium. In equilibrium I have 2,000, 2,000 and everyone is spending 65. You multiply the 65 minutes by 4,000 cars, you get 260,000 minutes. This is the social cost, if you like. The cost of everyone in terms of minutes. Can I make it lower? For instance, if 3,000 go like this and 3,000 go like this and 1,000 like this and 1,000 like this, is it going to be in total better? I say no, and we'll see how to solve it in general. But hold on a second. And how can I make sure that 3,000, that only 1,000 will go from here and from here? I can put toll. Okay, I charge fee. If you want to use this road, pay me. And I can raise the fee until I get here 1,000 and here's 3,000. So I may play with it using other instruments like toll. Okay? So can I do a better job? So let's look on this one. How much they spend? So the 3,000 here, it takes them 3,000 divided by 130 plus 45, 75 minutes each one of the 3,000 cars. So I look 3,000 times 75. Here it takes 45 minutes and 1,000 divided by 100, another 10, 55. So the other 1,000 spend 55 each, add up to 280. Not as good as the 260. Maybe another combination. So in order, if you want to really do it algebraically to prove, then you can look on this. Here it is. Here it is. D, C, A, B, X over 100, 45, 45, X over 100. So now I say, suppose Y will go from here. The same Y must continue because everyone goes from A to B. And so what is left? 4,000 minus Y. And 4,000 minus Y. And now I don't care about equilibrium. I don't care. I just want to see if this is, what is the Y that will make the total number of minutes minimum. So I look on, first of all, the cars that goes from A to C. How much they spend. So each one of them, you have to divide the number of cars by 100. But this is Y. X is now Y. So Y over 100, this is the time takes for every car to go from A to C. But how many cars are in this segment? Y. So this is the total. This is the time per car times how many cars? Y cars. Plus 45 minutes each one of the Y cars. So 45Y. Now this is going to AC, and this is going to CB. Plus, so let me call it T. Plus, let me go here, 45 times 4,000 minus Y, because 45 minutes it takes to go, and this is AD. AD. Let me make it nicer as much as I can. Okay. Y, every car spends here 45 minutes. How many cars there are? If Y went here, all the rest, 4,000 minus Y, went to D. All of them continue. So first of all, each car, how much they spend? The X is this. Plus 4,000 minus Y times 4,000 minus Y divide by 100. So let me just play a little bit with, so this is T equals Y square divide by 100. Now as you can see, the 45Y and 45 times negative Y cancel. So here I get 45 times 4,000 plus 180,000. And here I have to, what is this? This is actually 4,000 minus Y square divided by 100. Plus what? Divide by 100. If I have to take a square of this, first of all it's 4,000 square, which is, what is this? 16 million. Minus 2 times 4,000 times Y times 2, minus 8,000 Y, plus Y square. So let me take 100 out. So I have Y square and Y square. I have 2Y square. Now let me do the Y. Negative 8,000 Y plus a number. What is the number? So by the way, it's not 18 because I divide by 100, so I have to take 180,000 times 100, it is 18 million. 18 million plus the 16 million. Let me do it. So it is 18 million 100 times 180,000, it's 18 million plus 16 million, 34 million. Now, in order to minimize it, I want to minimize it. I don't care about equilibrium. I didn't say that the time to go ACB equal ADB. In order to minimize, I have to take the derivative and to set it to be 0. So it's 1 over 100. And here I have 4y, 2y squared, the derivative is 4y, minus 8,000. So it must be that y equals 2,000. What do we get? That the equilibrium is the most efficient one. Because in equilibrium, 2,000 went like this and 2,000 went like this. Remember I told you that in equilibrium is not necessarily the most efficient, is efficient. Princess dilemma, the equilibrium is inefficient. But in many we saw, when we computed Nash equilibrium, we saw that some Nash equilibrium are not efficient. But this Nash equilibrium of this specific diagram is efficient, because going 2,000 from here and 2,000 from here is when we this one minimizes the total, the social cost, the total number of minutes everyone spends. What do? We found we don't know how many to should go from C and how many from D. We put Y and then we say, okay, with this Y, what is the total cost? And let's find the Y that minimizes this total cost. The minimization is 2,000, but the 2,000 was exactly the equilibrium. So that's why we said before, the equilibrium here is efficient by chance, in the sense that there is no other traffic pattern with some other Y that reduces the total time spent on the road. In a second we'll see an equilibrium which is not efficient, but is efficient. Okay? Good. So that's what we have. And now let me clear it. And let's move on. Yeah, so actually we did this. Now, okay. Next, suppose that C is connected to D like before. And again, with a miracle road. Everything is the same. With a miracle road. Okay? In the most Next, suppose that C is connected to D in the most efficient way, so that it takes 0 minutes to cross the road CD, independently of the number of cars there, no matter what. Like 45 no matter what, 0 no matter what, 45 no matter what. By the way, if this means, it's a little bit strange example, it means that if you are the only one on the road, it takes you 0 minutes to go from A to B. Why? Or maybe almost 0. Why? If you are the only one, it takes you 1 over 100 of 1 minute, plus 0, plus you are the only one. 1, so it's not 1,000, it's 1. It's not 3,000, it's 1. So if you go like this, it will take you with the new road 1 over 100 plus 1 over 100, 1 over 50 of 1 minute. So it's about 1 second. It's about 1 second you can go with this example from A to B. But other than this, you spend at least 45 minutes. Either you go from like this or you go like this. So it's really amazing change. Okay? And now the question, let us first analyze the equilibrium pattern. With the new road, I say, okay, that no car will go like this and no car will go like this. What do I want to say? I claim that every car will go like this. So I say, if I go directly from A to D, it takes me 45 minutes. How long it will take me to go like this? In the worst case scenario, if I'm not the only one, moreover, everyone going here, okay? They really stuff the road AC. So how long it will take me to go from A to C in the worst case scenario? The worst case scenario is that the X is 4,000, everyone. So it will take me 40 minutes to go here and 0 here. So I can get from A to D in 40 minutes. Why should I go 45 minutes? And maybe I will get faster than 40 minutes. Because if not everyone goes like this, I'll spend less than 40 minutes. So the conclusion is that, let's read it together. Why? It will take a car 45 minutes to drive from A directly to D. On the other hand, it will take a car to drive to D through C at most 40 minutes, if all 4,000 cars drive to D through C. Therefore, in equilibrium, all 4,000 cars will go from A to C. Nobody, why should I use this one where at most I can spend at most 40 minutes to go to D through C and not directly, which takes 45 minutes. Therefore, in equilibrium, all 4,000 cars go from A to C.